Hi everyone. What we're going to discuss in this video are some main concepts from Calc 1. So the main topics overall that you look at in Calc 1 are limits, continuity, derivatives or differentiation, and integration. Okay? So when do you say the limit of a function as x approaches a exists? You say the limit as x approaches a of f of x exists if the limit from the left, this is the left because of the minus, as x approaches a f of x exists, and the limit from the right as x approaches a f of x exists, and these two values are equal, and this common limit is called the limit as x approaches a of f of x. Okay? Now, when do you say a function f is continuous at a point? A function f is continuous at a point x equals a if the limit as x approaches a exists and that limit is equal to the function value at a. Okay? So that's what you need for a function f to be continuous at x equals a. Okay, now you can generalize this to continuity on an open interval. When is a function continuous on an open interval? A function is continuous on an open interval if it's continuous at all the x's in that open interval. Okay? How about if you have a closed interval? You say a function f is continuous on a closed interval if it's continuous on the open interval, ab. And at a, we can only talk about limit from the left because you're talking only about a closed interval. There is a limit from the right. There is no left side of a. So you want that the limit from the right of f as x approaches a from the right is equal to f of a. So you call it that f is right continuous at a. And the limit from the left as x approaches b of f of x equals f of b. So it's left continuous at b. If you have that it's continuous on the open interval, right continuous at a, left continuous at b, then you say that f is continuous on the closed interval ab. Okay? Now, if you have a continuous function, so say you have a function f which is continuous on a closed interval, and you take any value z between f of a and f of b. F of a could be less than f of b or bigger than f of b. Okay, of course, if f of a equals f of b, then there is no z strictly between f of a and f of b, but you can just say that common value is z. Then there is a c in this interval ab such that f of c equals z. So if you have a function that's continuous, so let's draw a little picture. Okay, and you have some function like this. Oh, we should even take it the other way. Like this. Okay, this is b. So this is f of a. This is f of b. If you take any value z in this little green interval, so that's between f of a and f of b, then there has to be a c between a and b. So pick any z in there. So for example, pick this z in there. Then there has to be a c between a and b where f of c is equal to that z value. Okay, so that's what the intermediate value theorem says. You have a function continuous on a closed interval. Pick any value between f of a and f of b. There is a c such that f of c is that value. Okay? So those are the main concepts in continuity. How about differentiability or differentiation? We say a function f is differentiable at x equals a if this limit exists. The limit as x approaches a of f of x minus f of a over x minus a. Now, if you remember, if you just look at this part, what is that? If you have a, you have x, f of x minus f of a over x minus a is just the slope of the secant line, okay? So it's the slope of the line joining these 2 points on the graph. Now, as x approaches a from the left and x approaches a from the right, both of those should have have a limit. Their limit should be equal, and that will be this common limit. And so if that limit exists, then you say f is differentiable. Okay, instead of writing the limit like this, you could write x is a plus h, and as x approaches a, you will have that h goes to 0. So you could write this or this. This would be f prime of a, this is f prime of a, both are the same. Okay, these limits are the same, and this limit, if it exists, is called the derivative of f at a, and you denote it by f prime of a. Okay? Then let's look at a mean value theorem. Now suppose you have a function f which is continuous on a closed interval, okay? Differentiable on the open interval ab. Then if f of a equals f of b, there has to be a c between a and b such that f prime of c is f of b minus f of a over b minus a. B is not equal to a. So that's not 0, that's 0, so this is 0. So if f of b equals f of a, then there has to be a point in between where the derivative is 0. So the tangent line is horizontal. So as just one quick comment, as I said, this is the limit of the slopes of secant lines, so it'll be the slope of the tangent line. Okay, back to this mean value theorem. Okay, and that's called the Rolle's theorem when f of b equals f of a. More generally, f of b may not equal f of a. You have a function that's continuous on closed interval ab, differentiable on the open interval ab, then there has to be a c in ab such that the derivative at c, f prime of c, equals the slope of the secant line. Okay, so you can just take this picture that would explain it. Let's call this B. And what this says is there has to be some point C where the slope of the tangent line equals exactly the slope of the secant line. Okay? The slope of this line is f prime c. And the slope of this other line is f of b minus f of a over b minus a. Okay? So the mean value theorem says that there is a c between a and b where the slope of the tangent line equals the slope of the secant line. All right? So that's with differentiation. Now let's look at integration. You remember we have the limit of Riemann sums. We say a function is integrable if this limit exists, and if this limit exists, it is denoted by integral a to b f of x dx. Okay, where delta x is the width of the partition, xi star is any point in the ith subpartition, interval in the partition. Okay, so that is the definition of integrability. If a function f is continuous, then it is integrable. All right, so the definition of integrability is that this limit exists. Now, what this says is if the function is continuous, then it's integrable. There are other functions that are integrable that are not continuous, so you do not need that the function is continuous to be integrable. But if it's continuous, then it has to be integrable. All right? So many of the examples you see, you have that the function you're looking at is continuous. Okay? Now, what is this integral? Well, suppose you have a function's integrable, then what is this? This is the net signed area. between x equals a and x equals b and the x-axis. What is the net signed area? It is the area above the x-axis, below f, for when f is positive, and it's the area below the x-axis above f when f is negative, not minus. Sorry, minus the area below the x-axis above f. So the net signed area, it could be not continuous, but just for the ease of showing it to you, suppose you have a function like this, okay? And you have x equals a and x equals b. What is the integral from a to b going to give you? It's going to give you this yellow area. That's the area under f above the x-axis minus this green area. That's the area under the x-axis above f. Now it could be positive or negative depending on which area is larger. It could be 0 if they're both the same. Okay, so that's the net signed area. And that's what the integral will give you. Okay, so suppose you have a function that is continuous on an interval, and you look at the integral of the function over the interval and divide it by the length of the interval, you get the average value of the function on the interval. Okay, so we will call this the average value of f over the interval. All right, and the mean value theorem of integration, this is not the mean value theorem, it's a mean value theorem of integration. I just got a little lazy and I put the integral sign instead of writing it out. Says that if you have a function continuous on a closed interval, and you look at the average value, there must be a point in the interval where f of c equals that average value. Okay? So that's the mean value theorem of integration. It says there must be a c where f of c equals the average value, or we could say there must be a c where f of c times the length of the interval equals the integral. Either it's the same. Okay? That's the mean value theorem of integration. And the last two main ideas are fundamental theorem of calculus 1 and 2. If you have a function continuous on the closed interval, and you look at the function which is given by the net area from a to x under little f. So this is the net area from a to x under f, like the net signed area of from a to x of f. Call this function x. So this changes as x changes, this will change. Then this function that you've created will be differentiable, and its derivative will be little f. Okay? So if f is continuous, you create this function based on that little f from taking the definite integral from a to x. Call that f of x, capital F of x. This function, capital F of x, is differentiable, and its derivative equals the value of the function, little f at x over ab. Okay, so of course you also have that f prime is also going to be continuous. Okay, so this is, since f prime is f and f is continuous, f prime is continuous. Okay, and I didn't write this, but it's implicit that f is differentiable and f prime is equal to little f of x over ab. Okay, that's the fundamental theorem of calculus 1, and of course you could combine this with the chain rule where you have some function as a top limit or a function as the bottom limit, or two functions, some function as the bottom limit and the top limit. Then you'll have to use a chain rule in combination with this. All right. The second fundamental theorem of calculus says if you have a continuous function, f, little f, And capital F is any antiderivative. So what does that mean? Capital F prime is little f. Okay, so that means capital F is differentiable and its derivative is continuous, of course. Okay, but obviously if it's an antiderivative, you must have that it's differentiable. So you have capital F prime is little f. Then the integral of little f, this is called, also known as the net change theorem, will be capital F of B minus capital F of A. Okay? Another way to write this, which might be easier for you to remember, is integral A to B f prime of capital F prime of x dx is f of B minus f of A. Okay? So you have f prime is continuous on the closed interval. Then integral A to B f prime of x dx is f of B minus f of A. Okay? So those are some main ideas of the main topics we've looked at. Okay. Bye-bye.